Welcome back. In this video, we are stepping directly into the shoes of the great pioneer himself, Jacques Charles, to see exactly how he discovered the mathematical relationship between the volume and temperature of a gas. Imagine you are standing in a physics laboratory. On the screen, you can see a beautifully simple experimental setup. We have a very thin glass tube called a capillary tube. Inside this tube, we have trapped a column of perfectly dry air. But how did we trap it? We used a tiny liquid plug, a pellet of concentrated tetraoxosulfate 6-acid, or H₂SO₄. This acid pellet does two critical jobs. It absorbs any moisture to keep the air perfectly dry, and it acts as a tight, visible sealing that traps the gas underneath it. Now, look closely. This capillary tube and a thermometer are tied tightly to a wooden meter rule using two rubber bands. The whole setup is lowered into a large glass beaker of water, which acts as our controlled water bath. We also add a metal stirrer to circulate the water evenly, and at the bottom, a Bunsen burner stands ready to provide our source of heat. But before we strike a match, let us reveal a brilliant secret that makes this experiment work. A capillary tube is incredibly thin and completely uncalibrated, meaning it doesn't show volume lines. So, how do we measure the volume of the gas? Because the tube has a perfectly uniform cross-sectional area, the volume of the trapped air is directly proportional to its length. This means, by simply reading the height of the acid pellet using our meter rule, we are directly measuring the volume of the gas. Simple, elegant, and absolutely brilliant. At the start, we bring the initial temperature of the water down to exactly 0 degrees Celsius. At this precise freezing point, we look through the glass. The trapped air has an initial volume, which we record as V subscript 0. This is our baseline measurement. Now, we light the Bunsen burner as the orange flame heats the bottom of the beaker and our stirrer smoothly circulates the water. Watch what happens on the screen. The red line of mercury inside the thermometer begins to climb, showing a steady rise in temperature. Simultaneously, the heat transfers into the trapped air column. The gas molecules begin to dance with fierce kinetic energy, pushing violently upward. Look at the neon pink acid pellet. It begins to slide smoothly, gradually, and steadily upward along the meter rule. As the temperature increases, the length of the air column expands, showing us in real time that the volume of the gas is growing larger and larger with every single degree of heat added. Volume responds directly to temperature. If we record our readings at regular intervals, we get a beautiful, orderly table of values like the one appearing on your screen. In the first column, we have temperature, represented by a small letter T measured in degrees Celsius. It starts at 0 and progresses through temperature T1, T2, T3, up to any arbitrary final temperature, T. In the second column, we record our corresponding volumes measured in centimeters of length. At 0 degrees Celsius, our initial volume is V subscript 0. As the temperature rises to T1, the volume becomes V1. At T2, it becomes V2, matching every temperature step perfectly until it reaches our final volume, V subscript T. Now, what happens if we plot these coordinates onto a graph? Let us place volume on the vertical axis and temperature in degrees Celsius on the horizontal axis. When we link our data points together, nature draws a beautiful, perfectly straight line sloping upward. Notice exactly where this line begins. It does not start at the origin. It intersects the vertical volume axis at exactly V subscript 0, because even at 0 degrees Celsius, a gas still occupies a very real, measurable physical space. This straight line proves a profound truth. The expansion of a gas is completely uniform. But now, let us perform a daring mathematical thought experiment. What would happen if Instead of heating the gas, we began to cool it down far below freezing. Watch the graph carefully. If we take our beautiful straight line and extrapolate it, drawing a dashed path backward, down, down, through the freezing point, and deep into the sub-zero negatives, something extraordinary happens. The line falls downward until it crashes directly into the horizontal temperature axis at exactly minus 273 degrees Celsius. Look at that point on the graph. At minus 273 degrees Celsius, the vertical height drops to absolute zero. This means, theoretically, the volume of the gas completely vanishes. At this extreme depth of cold, minus 273 degrees Celsius, something extraordinary happens to matter. Look at the chamber on your screen. Under normal conditions, gas particles are wild, free, and constantly bouncing. But as we cool them down to the absolute limit, they lose every single drop of their kinetic energy. They can no longer fly. They can no longer bounce. They collapse completely to the floor of the container, locking together into a frozen, silent, motionless state. Because no substance can retain enough thermal energy to remain a gas at this temperature. Science honors this ultimate boundary as absolute zero. It is the temperature where all molecular motion stops and all gases cease to exist. Because of this disappearance of the gas, because no gas can exist at this temperature, because no substance can exist in a gaseous form at this temperature of minus 273 degrees Celsius, science honors this extreme temperature and extreme point as the absolute zero temperature, the lowest possible temperature in the entire universe. It is beautifully defined as the ultimate thermal boundary, the exact temperature at which all molecular motion stops and all gases cease to exist. Yes, the absolute zero temperature is defined as the temperature at which all gases cease to exist. Now, for the grand finale, let us use this beautiful graph to calculate the exact cubic expansivity of a gas represented by the Greek letter gamma. By definition, cubic expansivity is the change in volume divided by the initial volume, multiplied by the change in temperature. Let us calculate this using the geometry of our straight line. First, let us find the slope of the line from our freezing point up to our hot temperature. T, the rise in volume is Vt minus V0, and the run in temperature is T minus 0, which is simply T. So, our first slope is Vt minus V0 over T. Now, because it is a perfectly straight line, its slope is identical everywhere. Let us calculate the slope a second time, using our backward path from absolute zero up to our freezing point. The rise in volume from 0 to V0 is simply V0, and the run in temperature from minus 273 up to 0 is exactly 273. So, our second slope is V0 over 273. If we rewrite our cubic expansivity formula or expression and write the right-hand expression in two parts as Vt minus V0 over T multiplied by 1 over V0. Now, let us substitute the expression Vt minus V0 over T with 1 over V0 directly back into our original definition for cubic expansivity. Look at what happens on your screen. The term V0 in the numerator completely cancels out the V0 in the denominator. They vanish, leaving behind a single, universal, unchanging constant 1 over 273 per degree Celsius. This is the ultimate mathematical proof of Charles's law. It shows us exactly why every single gas in the universe expands by the exact same fraction of its volume for every degree rise in temperature. Nature's perfect symmetry, unlocked by pure mathematics. Thank you so much for joining us to decode the legendary principle known to science as Charles's law. Make sure to like this video, subscribe, and follow the Udimking Education Foundation on our official WhatsApp channel and social media networks. See you in the next class.
Udimking Education Foundation. Building confidence, ending examination malpractice for a better tomorrow.
We are building a better tomorrow.
Join us in shaping futures through integrity and education.